In this problem, we're asked to find the points of inflection and to determine intervals on which this function is concave up or concave down. We would begin by finding the points of inflection. So let's recall the definition for points of inflection. We have an inflection point of the function f of x at x equals c if the second derivative at c equals 0 or the second derivative at c does not exist, and after meeting one of these criteria, we know that additionally the concavity of the original function must switch about x equals c. So either it was concave up before x equals c and concave down after, or concave down before and then concave up after. So we'll begin by finding the second derivative. First we find the first derivative, and then from there we would find the second derivative. And we see the second derivative is just 6t. Now we might ask ourselves, when does 6t equal 0? Well, this occurs when t equals 0. And in this case, 6t will always be a value that exists, so we would only have a possible inflection point where this second derivative equals 0. Okay. Since the second derivative at 0 equals 0, we would say this is a possible inflection point. In order to be sure whether it's an inflection point or not, we would see, does the concavity switch about 0? We would do that with our second derivative test, so we would draw our number line. Since this will be labeled into the second derivative, we will say that this would be y double prime. Label our possible inflection point of 0, and then you pick test points in the intervals before and after. So in this case, test point in this interval might be -1, a test point here could be 1, and then we evaluate these in the second derivative. So at -1, the second derivative is -6, which is definitely less than 0. So the second derivative is negative there. Okay. Second derivative evaluated at 1 is 6, definitely a positive value. And then the conclusion is, since the second derivative is negative on the entire interval from -infinity to 0, we would know that the original function y is concave down on that interval. Since from 0 to infinity, the second derivative is always positive, we would say that the original function y is concave up on that interval. Based on this, we have verified that x equals 0 is indeed an inflection point because we have a change in concavity about x equals 0, and the second derivative at 0 was equal to 0. So we conclude that x equals 0 is an inflection point of this function. And then since we were asked about the intervals where it was concave up or concave down, we would just write that quickly. So from our second derivative test, we know it was concave down from -infinity to 0, concave up from 0 to +infinity.